Welcome to the lecture on PI/PD controller for SISO system. In our earlier lecture, we have seen the limitations of PID controller. Attempt will be made to design PI/PD controller by two methods in this lecture. Initially, we shall consider a plant transfer function of the form shown over here, which is having a numerator k and denominator s square plus alpha 1 s plus alpha 0. This all pole transfer function can assume different form depending on the values of alpha 1 and alpha 0. Now, when alpha 1 becomes 0, we get a second order integrating process. When alpha 1 equal to 0 and alpha 0 equal to 0, we get second order integrating process. Now, depending on the values of k also, we get the plant dynamics to be stable or unstable, but we shall assume a positive k for all the cases. Now, we shall design a PI/PD controller, which in block diagram form can be given as a PI controller having GC1S and the process dynamics given by GS, output denoted by YS and reference input by RS, and we have the feedback path, a negative feedback over here. Again, a controller in the inner feedback path given as GC2S is there. Now, this block diagram representation shows us the representation for a series feedback control scheme. This can equivalently be represented in the form of RS GC1S with a modified process given by G dash S and YS as the output. Now, G dash S is given by GS upon 1 plus GS GC2S. This modified process is being now controlled by a feed forward controller GC1S. Let us assume the form of the controllers to be of GC1S, a PI controller given by Kp 1 plus 1 upon TIS, and GC2S, a PD controller given by Kb plus TDS. Then we have got a PI/PD control structure, where we have got the feed forward path as well as inner feedback path controllers GC1S and GC2S respectively. Now, for the all pole system or plant transfer function k upon s square plus alpha 1 s plus alpha 0, when the PI and PD controller are employed, then the closed loop transfer function becomes T s equal to T I s plus 1 in the numerator divided by s cubed T I upon k K p plus alpha 1 plus k T d times T I s square upon k K p plus alpha 0 plus k K b plus k K p times T I s upon k K p plus 1. How do we get that closed loop transfer function? If we substitute G s equal to k upon s square plus alpha 1 s plus alpha 0 and the form of the GC1S and GC2S, then the closed loop transfer function can be obtained as shown over here. Now, G dash S can be obtained as k upon s square plus alpha 1 s plus alpha 0 divided by 1 plus k upon s square plus alpha 1 s plus alpha 0 times k b plus t d s, which can be simplified to the form of k upon s square plus alpha 1 plus k t d s plus alpha 0 plus k k b. The role of the inner feedback controller can be apparent from this G D S. Now, we see that with suitable choice of k b or design value of k b, it is possible to locate the poles of the modified transfer function at suitable locations. That is the benefit one gets by employing the inner controller GC2S. Had there been no GC2S, there is no scope for placing the poles of the original process at desired locations. So, KB and TD now enables one to locate the poles of the modified process or the original process at suitable locations with the help of GC2S. Now, the inner loop transfer function is to locate the poles of the modified process at desired locations, whereas the closed loop transfer function will give us in the form of closed loop transfer function now as G dash S G S G C 1 S upon 1 plus G dash S G C 1 S. So, which upon substitution will give us in the form of k k p T I S plus 1 over T I S times S square plus alpha 1 plus k T D S plus alpha 0 plus k k b plus k k p T I S plus 1. Now, this can further be simplified as T I S plus 1 in the numerator upon S square S cubed T I by k k p plus alpha 1 plus k T D T I upon k k p S square plus other terms that we have got here. So, the closed loop transfer function using the modified dynamics process dynamics G dash S gives us a transfer function with numerator T I S plus 1 and denominator H shown over here. Now, assuming k k p upon T I to be H beta cubed and S equal to beta S n, the closed loop transfer function can be expressed in the standard form given as T S n equal to C 1 S n plus 1 divided by S cubed plus D 2 S n square plus D 1 S n plus 1, where D 2 is alpha 1 plus k T D upon beta, D 1 is equal to alpha 0 plus k k b plus k k p upon beta square and C 1 equal to beta T I. Now, the closed loop transfer function has been obtained in the form of a standard transfer function of third order. Now, if C 1 is given or for a given C 1, we have got definite values of D 2 and D 1 as far as the third order transfer function is constant. Optimization of IST criterion results in optimum values of C1, D2 and D1 for the third order transfer function. Now, using this we have got now 4 inequalities. Now, D2, D1, C1 and k Kp upon Ti equal to beta cubed. These the four expressions 1, 2, 3 and 4. The 4 encircled expressions can be used to estimate the controller parameters k, Kp, Ti and Td. K, P, Ti, Kb, Td are the 4 unknowns in the controllers. So, both controllers GC1s and GC2 has got the unknowns Kp, Ti, Kb, Td. With the help of the 4 expressions or 4 inequalities, it is possible to estimate the 4 unknowns Kp, Ti, Kb, Td either by solving a set of linear equations or by employing some convenient technique. Now, let us try to design the controller parameters for a given process model. Given plant model parameters k equal to 2, alpha 1 equal to 0 and alpha 0 equal to -4, attempt will be made now to design the 4 controller parameters Kp, Ti, Kb and Td. Now, how the process model looks like? Now, Gs is equal to 2 upon S square minus 4. So, we have got a very difficult process, difficult in the sense the process has got one pole in the right half of the S plane. Now, I can write this in the form of S minus 2 and S plus 2. So, we have a pole located in the right half S plane, therefore, we have got an unstable process. Now, for this process to design the PI/PD controller, let us assume Kp to be 1 to limit the control signal. When the proportional controller magnitude is 1, that time the control signal will have less excursion. That is why we are assuming Kp to be 1. With that assumption of Kp equal to 1, as we see when Kp equal to 1, this expression will give us when Kp equal to 1, beta cubed will be equal to k upon Ti. Therefore, beta is equal to 2 upon Ti to the power 1 upon 3. Choosing Ti equal to 0.25 gives us beta equal to cube root of 8, that is equal to 2. Now, when beta equal to 2 and Ti equal to 0.25, C1 is equal to beta times Ti is equal to 0.5. Once we obtain C1, then using the graph for the optimized coefficients, we have got the plots for C1 versus D2 and D1 as you have seen earlier. So, using the value of C1, it is possible to obtain the optimum values of D2 and D1 for optimum step response performance of a closed loop system. Now, C1 equal to 0.5 gives us D2 equal to 1.595 and D1 equal to 2.12. These values are obtained from minimization of the IST criterion. Now, D2 is further expressed as alpha 1 plus k Td upon beta, which gives us Td equal to 1.595, because alpha 1 is known, which is equal to 0 and D2 is 1.595. So, this is equal to plus k Td, k is 2 2 times TD upon beta. So, beta is equal to 2. So, thus we get TD equal to 1.595. Similarly, D1 is estimated from the expression alpha 0 plus k kb plus k kp upon beta square is equal to that gives us kb equal to 5.24. Thus, the design values of the PIPD controller are obtained as Kp equal to 1, Ti equal to 0.25, Kb equal to 5.24 and Td equal to 1.595. So, applying some intuition, it is possible to estimate or design the parameters of a PIPD controller. One can resort to many techniques to obtain the PIPD parameters. As we have discussed earlier, one can solve the set of equations to obtain the 4 unknowns from the 4 expressions. Now, with these values of the PIPD controller, let us see the performance we get from the closed loop system. Thus, the PI controller is of this form and the PD controller of this form. For comparison, we have also designed a PID controller for beta equal to 1. We can have the same beta diameter irrespective of any value of beta. It is possible to design a PID controller using standard form. Now, the comparison of results are given here. When a unit step input is applied and a load disturbance of magnitude 0.1 is applied to the closed loop system, the output of the closed loop system is found to be of this form in the case of the PIPD controller and of this form for the PID controller. As evident from the responses, the PIPD controller is giving a quite satisfactory closed loop performance for both set point as well as load disturbance inputs, as the overshoot, settling time when compared with the PID controller are found to be very small, and the overall performance of the closed loop system as far as the PIPD controller is concerned is found to be extremely improved one and desirable one as far as the PID controller is concerned. Now, we shall go through some more illustrative examples. Let us consider one more example where the process is assumed to have a third order dynamics of this form. G s is equal to 1 upon s plus 1 to the power 3. So, for this third order stable process, PIPD, PI with D in the feedback path and PID controllers are designed by ISTE optimization. Not necessarily one has to resort to the standard form technique to design the PIPD, PID and PID parameters. So, by ISTE optimization using some routine, it is possible to design the parameters of a PIPD controller, PI with D controller and PID controller. Similarly, a PID controller designed by some other technique, Astrom and Hoagland method is also considered in this simulation study. Now, the simulation results are shown here, where again it shows that the PIPD controller response given by the solid line in this plot outperforms the responses or performances given by other methods. The control signal given by different methods are also shown over here, and the plot shows that the PIPD controller gives us improved control variations. So, less control effort is employed to obtain superior performance compared to other controllers. This is the benefit one get from the PIPD controllers. In this example, an unstable first order plus time delay plant with transfer function given by 4 e to the power minus 2 s upon 4 s minus 1 is considered. So, for this unstable process with time delay also PIPD controller is designed and a PIDP controller is designed by some other technique. This is also a 4 parameter controller. A PIPD controller is a 4 parameter controller. We have got 4 parameters in the controller. Similarly, the PIDP controller of Park et al. Is also having 4 parameters. So, for fair comparison, the results given by Park et al.'s method and the PIPD controller designed by our method is shown in the figure given in the left side. Then, as expected, the results obtained by the 4 parameter PIPD controller designed by standard firm is better than that is obtainable by Park et al.'s method. Next, the second figure shows the responses given by various PID controllers. A PID controller, a PI with D in the feedback path controller are designed by IST optimization and another PID controller is designed by Valentine et al.'s method. All the results are included in the second figure. So, the second figure shows the results given, the step responses performances given by the different PID controllers. So, suddenly if we compare the responses given in the left hand side and the right hand side figures, as expected, the PIPD controllers outperform the performances given by PID controllers, because not only we have got one extra parameter in the PIPD controller, the PIPD controller is not subjected to structural limitations. That is why we have got better or superior responses compared to the PID controllers. Next, we shall attempt to design a PIPD controller for integrating processes. Earlier, we have seen how PIPD controllers are useful for not only stable, but also for unstable processes with or without time delay. Now, attempt will be made to design a PIPD controller for integrating processes. So, consider the process model transfer function to be of the form k e to the power minus theta s upon s times T1 s plus 1. So, this gives us the transfer function model of an integrating second order integrating process, and integrating not only a second order integrating process. And let us assume the form of the PIPD controllers to be of the form of GC1 as given by Kp times 1 plus 1 upon TIS, the standard PI controller, whereas the PD controller in the feedback path is assumed to have the form Kb plus TDS. But for ease in analysis of closed loop system, often it is useful to assume the form of this controller GC2 S H Kb times 1 plus TDS. So, without loss of generality, one can get the inner feedback controller in this form, because if you multiply this, we get it is k b plus k b t d s, which can ultimately be expressed in the form of k b plus t d dash s. So, it is all about expressing the derivative value in some different form. So, that way without loss of generality, let us assume the form of the PD controller to be of the form of GC2 S is equal to KB1 plus TDS. So, with this choice of the controllers GC1S and GC2S and the assumed form of the process dynamics, the loop gain, as far as the inner loop gain is concerned, the loop gain can be written as GC2S GS, which is equal to K KB e to the power minus theta s upon s, when T d is equal to T 1. So, that is where we are choosing a convenient form of the controller GC2S. The GC2S is defined in this form for the sake of cancellation of the 0 of the controller with a pole of the process. Then the loop gain, this is the inner loop gain, we can say the inner loop gain of the system is given by k k b e to the power minus theta s upon s, when T d is equal to T 1. Then at phase crossover frequency, at phase crossover frequency, let the frequency be denoted by omega p. The loop gain GC to G j omega p will give us an angle of minus pi by 2 minus theta omega p, and which is to be equal to minus pi, because we are considering the phase crossover point at which the loop phase is minus 180 degree or minus pi. So, this expression gives us omega p is equal to pi upon 2 theta. So, this is one relation we get using the loop gain. Similarly, at the same phase crossover frequency, magnitude of the loop gain GC2 G j omega p magnitude is equal to k k b by omega p, which is nothing but inverse of the gain margin, is equal to 1 upon a m. This is by definition we get the definition of gain margin for the loop gain gives us this expression. So, from here we get k k b is equal to omega p upon a m, but omega p is equal to pi upon 2 theta. Therefore, this can be written as pi upon 2 theta a m. So, thus we have got a relation which is relating the unknown k b with the gain margin of the loop. Then using this, it is possible to design k b. Now, next the stabilized process G dash S is equal to G s upon 1 plus G s G c 2 s, which can be written as k e to the power minus theta s upon s times t 1 s plus 1 divided by 1 plus k e to the power minus theta s upon s times t 1 s plus 1 times k b t d s plus 1. G dash s further can be simplified and written in the form of k e to the power minus theta s, k e to the power minus theta s upon t 1 s plus 1 s plus k k b e to the power minus theta s. Please keep in mind that T d is equal to T 1. With that assumption only we get this reduced form of the modified transfer function for the plant. Now, this with the assumption of e to the power minus theta s is equal to 1 minus theta s, g dash s further can be written as k e to the power minus theta s times T 1 s plus 1 s plus k k b 1 minus theta s, which further can be simplified and written in the form of k e to the power minus theta s upon T 1 s plus 1 times 1 minus k k b theta s plus k k b k k b. So, k k b. So, what we see from here, the modified process has got poles located at minus 1 upon T 1 and minus k k b upon 1 minus k k b theta. Now, T 1 is the process parameter, we have no hold over that, and T 1 is assumed to be 0, but we do not know about the magnitude of T 1, value of T 1, but anyhow the pole is located in the left half of the S plane. Now, with the design, suitable design of k b, it is possible to locate the other pole of the modified process at suitable locations, that is at far left in the S plane, far left in the S plane. Oh, that is possible when we choose a large value for the number, or when this becomes a large number. That means, now let tau equal to 1 minus k k b theta upon k k b. So, when tau is small, then this is going to be a large negative number, and thus the pole is pushed far left of the S plane. That is what we wish. So, the tau has to be a small number. Now, we shall consider the loop gain of the overall loop now for designing the remaining parameters of the PIPD controller. Now, the overall loop gain, is given by G dash S G C 1 S is equal to k e to the power minus theta s times T 1 s plus 1 minus k k b theta s plus k k b times k b k p T I s plus 1 upon T I s. Again, let T I is equal to T 1. Why do we take such assumptions? for ease in analysis of the overall loop gain, it is desirable to make this assumption. So, with this assumption the loop gain becomes G dash S G C 1 S is equal to K K P e to the power minus theta s times T 1 S times K K B times tau s plus 1. Okay. So, with this loop gain, using the phase margin condition, it is possible to design the unknown K p. At gain crossover frequency, which is denoted by omega g, the loop gain becomes K P upon T 1 omega g root of tau square omega g square plus 1 is equal to 1, because at this frequency the loop gain is equal to 1, that is what we have expressed. So, this loop gain equal to 1 condition gives us K K P upon T 1 omega g root of tau square omega g square plus 1 is equal to 1. But earlier we have seen that to push the pole of the closed loop system to far left of the S plane, tau has to be a small number. So, tau is a small number. So, with that assumption, this expression can be simplified and written as K K P upon T 1 omega g is equal to 1. Oh, this K B is missing here. So, that way that will give us omega g is equal to K K P upon K K B and T 1. Here K is also missing. So, that way this will give us K K B K K P upon K K B T 1 omega g, yes, root of tau square omega g square plus 1 is equal to 1. So, thus we are getting the gain crossover frequency expressed in the form of K K P upon K K B T 1. So, let us rewrite that once more. The loop gain at gain crossover frequency gives us the expression omega g is equal to K K P upon K K B T 1. Now, the phase margin at the gain crossover frequency further results in an expression which can be expressed as phase margin is equal to pi minus pi by 2 minus theta omega g minus tan inverse omega g tau. But because tau is small, we know that tau is small, therefore, this can be expressed as pi by 2 minus theta omega g minus omega g tau. So, upon simplification, one will get the omega g in the form of pi by 2 minus phase margin divided by theta plus tau. But omega g already we have got in this form. So, upon comparison it is possible to get this is equal to again K K P upon K K B T 1, which gives us the expression for k kph, k kb T1 pi by 2 minus phase margin upon theta plus tau. So, we have got one more expression for the k kp. Earlier we have made the assumption, please keep in mind that those assumptions are T I is equal to T D is equal to T 1. So, already we know two parameters of the PIPD controllers, those parameters are T I and T D. So, rest we need to estimate the remaining two unknowns K P and K B. So, K P is estimated using this expression and with the choice for a phase margin, and the K B is estimated using this expression, K B is estimated using this expression and with a choice of gain margin. So, given gain and choosing certain gain and phase margins and using equation 2 and 3, it is possible to design the remaining two unknowns of the PIPD controller. So, using 2 and 3, it is possible to design the parameters K P using expression 3 and K B using the expression 2. Of course, with the choice of certain phase and gain margins. Let us design PIPD controller for a second order integrating process. Let us assume that the second order integrating process is given by 5 upon s times 2s plus 1 with a time delay of e to the power minus 0.5 s. So, we have a time delay of 0.5 seconds and the time constant at t 1 equal to 2 seconds and k equal to 5 and theta equal to 0.5 seconds. So, these are the given parameters. Let us choose the phase and gain margins to be phase margin is equal to 45 degree, that means pi by 4, and gain margin AM is equal to 3. So, with these choices of phase and gain margins, using the expressions 2 and 3, we will be able to estimate the unknown parameters of the controller. Now, KB is equal to pi upon 2 theta AM k. So, in our case now it is pi upon 2 into 0.5 into 3 into 5. That gives us kbh pi upon 15 is equal to kbh 0.20. So, that will come out to be 0.2094. So, thus we have got the design value of the kb shown over here 0.2094. Similarly, Kp is estimated using expression 3. So, upon substitution of K T1 phi m, which is nothing but pi upon 4, theta 0.5 and tau, expression for the tau is given over here. So, we have assumed the tau to be of this form. So, substituting all those values in 3, we get Kp as 0.3445. So, it is not difficult to design the unknown parameters for the PIPD controllers using the phase and gain margin conditions. Now, as we know TD is equal to Ti is equal to T1, which is nothing but 2. So, those values are also shown over here. So, Kp Ti is equal to 2, therefore, 1 upon Ti is equal to 0.5 shown over here. Now, Td is 2, Td is equal to Ti is equal to T1, therefore, Td is equal to 2. So, thus all the parameters associated with the PIPD controllers are estimated and put in this simulation diagram. The simulation diagram shows the process model given as 5 e to the power minus 0.5 s, delay is 0.5 s upon 2 s square plus s. This is the process. Now, the PD controller has got the parameters Kb times. Please keep in mind it is the form of the GC2S. GC2S is Kb 1 plus TDS. So, in the diagram it is 0.2094 times 1 plus 2s, which can be shown in the Simulink in this form. This is 1, then plus 2s is coming over here, is multiplied with the gain 0.2094. Thus, we get the GC2s given by this. So, this is what we have got the GC2s, and the upper one is GS. Now, the PI controller parameters are given here and the PI controller is implemented here in this form GC1S. Thus, we have got the PIPD controller GC1S, GC2S and the process, and the simulation diagram now gives us the results. The step responses and the load disturbance responses are shown over here. Is very nice responses as far as the phase and gain margins are concerned. Now, since we have chosen suitable phase and gain margin, it is expected that we shall get robust performances from the closed loop system. That is shown by this diagram. When the time constant T1 is changed by plus minus 20% also, the responses do not vary by very much. This is what we get when the time constant is changing by 20%, and this is the response we get when the time constant is changing by minus 20%. So, the responses show us that we have got robust performances given by the PIPD controllers. Now, when the time, not only the time constant, when the steady state gain of the process is also changed. In spite of the changes, the closed loop system is expected to expected to be subjected to better performances, since the PIPD controller has been designed based on suitable phase and gain margins. Now, there are some illustrative examples also. Consider an integrating process dynamics, a fourth order integrating process dynamics. For that also, the PIPD controller responses given by the solid line is found to be improved one compared to the 4 parameter PIDP control of Quack et al. And PID controller by IST optimization and PID controller designed by Ziegler-Nichols method. So, we get improved performances not only for integrating processes, also we get improved performances of PIPD controller for resonant processes also. Let us consider this resonating process. For this also the PIPD controller response given by the solid line is found to be superior compared to the PID and PID designed by IST optimization and PID controller designed by Ostrom-Hogland method. Now, Ostrom-Hogland method is giving a very poor set point response, whereas the PIPD controller is expected is giving quite superior responses. In summary, I can say that PID controller has got structural limitations in controlling unstable and integrating processes, whereas PIPD controller can successfully control resonating, unstable, integrating processes. The extra control parameter is leading to stupendous superior performances by splitting the proportional controller that is there in the feed forward path. Derivative controller in the feedback path not only provides compensation, but also overcomes derivative kick often found in many practical control systems. So, the PIPD controller is superior to PID controller in controlling particularly unstable, integrating and resonating processes. Now, some points to ponder. One may ask, can the standard form based PIPD controller design be extended to processes with time delay? Yes, the PIPD controller can be extended to processes with time delay, but when a standard form based PIPD controller design is made, at that time the time delay need to be approximated, and one can make use of either Taylor series expression or paid approximation for the time delay term. But when the time delay is quite large, Smith predictor controller may be used, in which case there is no need for approximations to time delay, and the PIPD controllers can be designed conveniently using the standard form. Second point may be raised, are the performances given by PIPD controller improved always than that obtainable with a PID controller? Yes, due to the additional controller parameter in the PIPD controller than the PID controller, the PIPD controller result in better performances. Splitting of the proportional controller results in significantly improved closed loop performances. That is all in this lecture.